Swayam Prabha. Digital India. Educated India.
Hello everyone, so welcome to a sixth lecture on tutorial session of Geology and Soil Mechanics. So we are discussing here a problem on consolidation, which basically stated that there was an embankment of height 4 meter, height 2.4 meter below a clay layer of 4 meter. So the figure was this height was given as 4 meter. This embankment height was given as 2.4 meter. The gamma of embankment was given as 21 kilonewton per meter cube. Basically this is the gamma B or the bulk gamma. The water table was at the top of the clay layer, and below it this clay layer was a sandy gravel layer. Now it was said that that basically sample was extruded from 2 meter below the water table, that means at the mid height of the clay layer, and a consolidation test was carried out whose results were plotted, and we found out that what was the compression index, the coefficient of consolidation, and also the settlement. Now it was also asked in the question that the settlement was actually concluded after 2 years, but it was asked that the settlement is to be concluded in 4 months. In that case, what was the height of embankment? So in that case we found out that the total settlement height, or the total settlement height was 34 centimeter for a clay layer of thickness of 4 meter. Now if the settlement height was 34 centimeter, then we said that in this case, from the equation of the total time, that is TV is equal to CV into H square into T, where H is basically the drainage path length. So in this case the drainage path length is to be halved, because the drainage is both in the bottom as well as in the top direction. So the drainage of clay layer is both in both directions, so H is actually equivalent to H by 2, or equivalent to 2 meter, because the height of the clay layer by 2, so equivalent to 2 meter. So we said that T is equal to TV into H square by CV, which is equivalent to 2 into 100 square into TV by CV. Now we also said in the previous lecture that 100% of the settlement is reached in infinite time. That means it takes a very long time to reach the 100% of settlement. So theoretically it is suggested that at 99.4% generally the 100% of the settlement is reached. So if the U, or the degree of consolidation, is actually equivalent to 99.4%, then you can find out from formula that TV is equivalent to 2. So putting that value in the previous expression, we get 2 into 100 square into 2 by CV. Now CV we found it out by log time method. There is another method that basically is called square root of time method, and from log time method we found it out that the coefficient of CV is the coefficient of consolidation, or basically CV, is equivalent to 1.15 into 10 to the power minus 3. Now you can also adopt the square root of time method if you think that that is more suitable. And in this case we came to the conclusion that the total time required for the clay layer to reach a settlement of 34 centimeter is actually equivalent to 805 days, which is equivalent to 2 years, 2 months and 15 days. Now, practically you can see that this is a very long time that is required for the settlement of 34 centimeter to reach. So, in that case you can reduce the height of the embankment in order to achieve the settlement in 4 months. So, in order to achieve the settlement in 4 months, or let us say 120 days, what we said was that we just recalculated TV. So, in this case TV is equal to CV into T by H square, and we already know that T is equivalent to 120 days. We also know that H is 200 centimeter and CV is 1.15 into 10 to the power minus 3, because it is the same clay layer. So, from there we calculated TV equivalent to 0.298 or equivalent to 0.30. Now, from TV we can actually calculate the degree of consolidation. So, because there is a formula between TV and U, so from TV back calculate, if you back calculate the degree of consolidation, it comes out to be 0.613. So, delta H equal to 34 centimeter would actually now correspond to 61.3% of the total consolidation settlement. Now, 61.3% of the consolidation settlement would be obtained under a surcharge of under a heavier surcharge. So, in this case basically it will be equivalent to 0.34 meter divided by 0.613, because 61.3% correspond to 34 centimeters. So, the total settlement would correspond to 55 meter. So, now this is the 55 meter is the total settlement. The settlement of 34 centimeter corresponds to 61.3% of the settlement S that would be obtained under heavier surcharge. So, in this case the settlement would be equivalent to 54 meter. The total settlement would be equivalent to 55 centimeter. So, now moving back to the previous formula for the settlement, we know that H into Cc by 1 plus E naught into log sigma naught dash plus del sigma by sigma naught dash. This is what is the formula for settlement if you ignore the pre-consolidation settlement, if you ignore that the settlement is totally due to the virgin consolidation curve. So, in that case log of sigma naught dash plus del sigma by sigma naught dash would be equivalent to S into 1 plus E naught by H into Cc. Now, already found it out the value of the compression index or the Cc from our previous lecture. The value of the compression index was found out to be equivalent to 2.1. H, as we all know, it is 4 meter, because the total thickness of the clay layer is 4 meter, and E naught, that also we said in the previous lecture, was found out to be equivalent to 1.86. And now you already know that the total settlement is 0.55 meter, corresponding to a 61.3% settlement, corresponding to a 61.3% consolidation for a settlement of 34 centimeter. So, just plug the values and you will get log of sigma naught dash plus del sigma by sigma naught dash as 55 into 2.86 divided by 4 into 100 into 2.1, which is equivalent to 0.187. So, from here you already know what is the value of sigma naught dash is, because sigma naught dash is basically the stress at the mid height of the clay layer. So, the stress at the mid height of the clay layer corresponds to a value of 0.12 DA Newton per centimeter square, or basically 12 kPa. That is what is the stress at the mid height of the clay layer is. Now, if the stress at the mid height of the clay layer is 12 kPa, then log of 12 plus del sigma by 12 corresponds to 0.187. So, from there del sigma comes out to be 0.65 da Newton per centimeter square or 65 kPa. So, this is the extra stress that is imparted on the clay layer. So, that means if this is the clay layer, if the height of the embankment is h, then gamma, which is the density of the embankment, which is gamma b into h, must be equivalent to 65 kPa. Now, as we all know, gamma b is already equivalent to 21 kilonewton per meter cube. So, h is 65 by 21, that is equivalent to 3.10 meter. The surcharge, that is del h, will be equivalent to 3.10 minus 2.40 into 0.70, because 2.4 is the previous height of the embankment. The previous height of the embankment is 2.40. This is already said here. So, this is the extra surcharge that is to be needed in order to achieve a settlement of 34 centimeter within 4 months. So, you can see from this example that how it is possible to quickly stabilize an embankment if you add an surcharge. So, often this is done with vacuum, and this type of technique is termed as a vacuum preloading. In certain cases you will see that, in certain cases in the field you will see that basically you have to achieve a settlement, you have to achieve a desired settlement within a very short period of time. In that case you need an extra surcharge, and this surcharge is calculated, and the surcharge that is needed in order to achieve the required settlement is calculated in the same fashion as it is shown in this example. So, in this case basically pre-consolidation, generally the process of pre-consolidation or basically applying a surcharge in order to achieve the desired consolidation is programmed. In this case, a surcharge of 70 centimeter, if you keep it for a period of 4 months and then remove it, would accelerate the settlement, and it would achieve the desired settlement of, let us say, 34 centimeter within the required time. So, you no need to wait for the period of 2 years, 2 months and 15 days, rather you would add an extra surcharge rather on this clay layer of 4 meter, and on this embankment of height 2.4 meter, you would add an extra surcharge of 0.7 meter and accelerate this settlement to 34 centimeter within the period of 4 months. After that you can remove this 0.7 meter and since the total settlement that is achievable under this type of surcharge, under this type of embankment is actually 34 centimeter. So, this surcharge will be, so this settlement will be achieved within 4 months rather than waiting for 2 years or 2 years, 2 months and 15 days. So, this is a way in which a ground improvement technique is done. Now, as we know that under all soils, almost under loads, almost all soils will cause settlement of structures. Now, one of the most important thing that you have to see while performing a consolidation settlement is that whether the settlement is within the desired limit or not. Now, different codes have specified different values for the settlement within the desirable limit, and if the settlement is within the tolerable limit, then only you can design that structure, otherwise not. So, structures, and one of the most important fact is also that there is not only a single type of settlement like a consolidated settlement, there is also a part called differential settlement. That means different parts of the structure may settle differently under loads. So, let us say that this is a column and there is another column here. Now, if this part of the soil due to some very fine layer of clay may settle differently than this part of the structure, then the settlement at B would be greater than A. In that case, the structure may settle differently under the same load. Basically, the load imparted on the structure is same. So, the settlement of B is greater than settlement of A. In this case, a differential settlement is introduced. Now, a differential settlement is very dangerous compared to the general consolidation settlement. It may induce cracks in the structure because the two parts of the structure settle differently, and it is very crucial when basically you are designing a structure. An example, a very good example of the differential settlement is, as you all know, is Leaning Tower of Pisa. Now, in this case, at the end of the 1178, when the structure was completed, the tower began settling differently. The foundation in that case let us say if this is the structure, then this is 3 meter of silty sand, and this was a clay layer that was 30 meter of soft clay. Now, this 30 meter of soft clay was the only reason why basically it caused the differential settlement. Now, we are not going to discuss in details about the case study here, but we are going to carry out an exactly a different type of problem on a differential settlement in order to make you aware of about how a differential settlement is detrimental for the cause of the structure. So, let us say a second problem is basically on a foundation or the same type of column load that I showed you. So, foundations of two supporting columns are shown below, just like the same type of thing that I showed you just earlier. So, a load of 780 kilonewton, the load is same in both the column, and this is of width 1.5 meter. The foundations are also same, both the foundations are of width 1.5 meter into 1.5 meter. This is a layer of sand. Now, as you see, as I have said in the previous problem also, that the clay layer may not be uniform just below. The clay layer may be different below one foundation and may be different below the other foundation. That is one of the major reasons why the soil investigation is to be carried out very accurately. Otherwise, the differential settlement may affect the structure very much. So, this is a clay layer which has an MV of 0.7 meter square per meganewton. Now, this height is given as 1.4 meter, while this height is given as 3 meter. This height is again given as 1.2 meter. This height is obviously 2.8 meter. Now, this is due to an extensive soil investigation that this type of profile is obtained. So, it is assumed in the design of foundations that the clay layer had a uniform thickness of 1.2 meter. So, this is the reason, because you see that the extensive soil investigation was only carried out below one of the foundations. So, if below one of the foundations only extensive soil investigation is carried out and below the other one, if the extensive soil investigation is not carried out, in this case you will assume the clay layer is actually uniform. For this case, actually what is done is that you have to carry out, or you have to perform different boreholes, or in order to get the soil profile you have to dig at different points within the profile. So, let us say a point A, point B, a point C. In these cases you will know that whether the layer below, whether different layers below are actually of uniform thickness or not. In this case basically it was one of the faulty constructions, because in this case the tail layer was assumed to be uniform or thickness of 1.2 meter. So that is why what happened was that 2 years after construction, the building settled with a differential settlement of 10 millimeter. So it's obvious from the soil profile that there would be a different settlement, because the clay layer is thicker here more while the clay layer is thicker here less. So this different settlement now caused walls of the building to crack, and door jamming and other things, because the settlement here in below the second column was more. So obviously this column had this settlement settled more. So that is why all those things, this cracking and all those phenomena came up. So that is why I said that differential settlement is very detrimental to the structures. So you have to perform a very proper soil investigation in order to know that whether there will be a differential settlement or not. Different codes have also specified different measurements of different settlement. So there is only a particular limit to the differential settlement that you can actually approve in the field. So in this case, what you have to do is that we have to first find out that what is the vertical stress increase at the center of clay layer under each foundation. That means the stress increase just at the mid height of this layer and just at the mid height of this layer. You have to find out that what is the stress increase below each layer. So now a general formula that we will take from here will be discussed in the next subsequent lectures, that is the effect of stress, that is effective of stress on soil, the Bouzinek's method. So under let me discuss just a little bit of it here. So basically if there is a rectangular footing, let us say in 3 dimensions, with the breadth of B and a length of L, in that case the extra stress that is imparted to the soil at a depth Z is equivalent to, due to a load P, is actually equivalent to P by B plus Z into L plus Z, if you consider it to be if you consider the distribution to be at 45 degree, that is if you consider the distribution to be at equivalent in both the directions. So this is a general formula that will take help here. In general case you are not able to find out that what is the delta sigma Z. In all the previous problems that we have discussed, actually we have either said about delta sigma Z or just an extra load was imparted on the soil layer, but in this case it is a footing, and generally you are asked to find out that what is the extra stress increase below a footing. So this is a general formula. If it is a rectangular footing or a square footing, this is a general formula how you can find out that what is the extra stress that is imparted due to the load that is coming on the footing at a certain depth below. So in this case we will take up of this formula, that delta sigma Z is equal to P, where P is the load, B is the width of the footing, and L is the length of the footing. Now obviously B and L are here equivalent, because we have said that the footing is of length and width, is a square footing of length and width 1.5 meter into 1.5 meter. So P by 1.5 plus Z to 1.5 plus Z. Now let us look that what is the mid height of the clay layer is at. Now for the first footing, the Z is actually 3 plus 1.2 by 2, so equivalent to 3.6 meter, while for the second footing it is Z is equivalent to 1.4 plus 2.8 by 2, so equivalent to 2.8 meter. So, delta sigma z for footing number, let us now name this as footing A and B. So, for footing A it is equivalent to P by 1.5 plus, now Z for first footing is 3.6. So, 1.5 plus 3.6 square. Now, P is 780 kilonewton. So, 1.5 plus 3.6 square equivalent to 30 kPa. So, this is the extra stress that is imparted in the clay layer due to the load on the footing. And B 1.5 plus 2.8 square to 42.2 kPa. So, these are the two stresses, the increment of stress at the clay layer, just at the mid height of the clay layer for the footing A and B. Now, for more accurate, as I have said previously also, that if you want to consider a more accurate distribution of the stress or the settlement, what you have to do is that you have to divide this clay layer. You have to divide this clay layer into number of segments as you wish. You can divide this into 2 segments, you can divide this into 4 segments, whatever you want. In that case, the stress calculation as well as the settlement calculation would be more accurate. Now just a simple formula for calculation of the primary consolidation settlement, because in this case we will not consider any secondary effects, or this case we will consider only the virgin consolidation curve and we will not consider any pre-consolidation settlement. So, no over consolidated soil is present here, just a normally consolidated soil is present here. So, no over consolidation settlement calculations are done here. Now, as I have said that settlement calculations can be done in 2 ways, either using the MV formula, MV is equal to AV by 1 plus E naught, which is equivalent to delta E by delta sigma into 1 plus E naught, and this delta E by delta sigma is equivalent to delta E delta H by H. So, delta H is actually equivalent to MV into H into delta sigma, either by this way, or you can go by delta H is equal to Cc by 1 plus E naught into H into log of sigma naught plus del sigma by sigma naught. Any one of them, if your settlement is within the virgin consolidation curve, or basically if your settlement is here in this virgin consolidation curve after the pre-consolidation pressure, after sigma p dash or sigma naught dash is greater than sigma p dash, in that case you can use any one of these above formula to calculate the settlement. So, here we are going to adopt the method of MV, or the coefficient of volume compressibility method. So, delta H is equal to MV into H into delta sigma, because MV is already given to us in the question. MV is 0.7 meter square per mega Newton. So, MV is given to us in the question. So, for delta H for footing A will be equivalent to MV into H into delta sigma. So, 1.2 into 0.7 into 10 to the power minus 3 into 30. The stress increase is 30 and the layer thickness is 1.2. So, that is why H is 1.2. MV we have already said it is 0.7 meter square per mega Newton. So, in order to convert into appropriate units, we have considered to 0.7 10 to the power minus 3. So, 25.2 millimeter. This is the settlement under the footing A. Similarly, you can find out using the coefficient of volume compressibility settlement under the footing B. In this case, the clay layer is of thickness 2.8 meter. So, 2.8 into 0.7 into 10 to the power minus 3 into 42.2, because that is the extra stress that comes due to the load on the footing B. So, in this case it comes out to be 82.7 millimeter. Now, just consider that if you had considered the clay layer to be of uniform thickness, then your settlement would have been 25.2 millimeter throughout. But now, as I have said also previously, that your settlement below footing B is more. So in this case the settlement below footing B has come out to be 82.7 millimeter, and if you consider it to be uniform, then your settlement was 25.2, because that is what is the settlement under footing A. So this comes out to be equivalent to 57.5 millimeter. So an extra settlement of 57.5 millimeter occurs under footing B. Now generally the code prefers a defense settlement of 24 millimeter. So if you consider the 24 millimeter defense settlement, or 10 millimeter, let us say, 24 millimeter defense settlement, so this is obviously greater than 24 millimeter defense settlement. So you cannot construct a building like this. I mean, you cannot construct a building of the clay layer just with a defense settlement of 57.5 millimeter. So the next question that comes here is that calculate the time for millimeter differential settlement to occur if current differential settlement is 10 millimeter, because they have asked to find out the 24 millimeter differential settlement, because that is the limit within which you should restrict your defense settlement. So at present the defense settlement is ongoing in the structure, because this is the ultimate defense settlement that we have found out, 57.5, because as you know, these formulas are basically to find out the ultimate settlement. So obviously this defense settlement is the ultimate defense settlement. Now since you are asked to find out that, now in the ongoing process basically the defense settlement is right now 10 millimeter, and you are asked to find out the defense settlement for 24 millimeter. So let us first find out, just like the previous problem, as we have said, that you have to find out the extra load that is imparted to find out a settlement that is to be caused within the 4 months. Here also similarly you have found out the degree of consolidation in that case. So here also similarly you will find out the what is the degree of consolidation at present going on in the soil. So in the soil the present degree of consolidation can be given by delta ultimate. Delta is the present defense settlement, delta ultimate is the final defense settlement. This is equivalent to 10 by 57.5, so this is equivalent to 0.17. So at present 17% of the total defense settlement is going on. So now TV is equal to 4 by pi into u square, because you all know this is 17%, because you all know that for u less than 60% the formula for TV is pi by 4 into u by 100 square. That is the same thing that we are applying here. So if you just rearrange the numerators and denominators, you will come across TV is equal to 4 by pi into u square, 4 by pi into u by 100 square. So this is equivalent to 4 by pi into 0.17 square, because 17% the defense settlement, so 0.037. So your TV comes out to be 0.037. Now from TV we will calculate the coefficient of consolidation. So TV into h square by t, the formula for coefficient of degree of consolidation. So TV, as we all know, we have found it out to be 0.037 into h square by t. Now let us look at the soil profile before we find out the h square. Now below this is a gravel layer. So obviously, like the previous case, since the top is covered with sand and below since there is a gravel, so like just before the previous case, this is also a double drainage problem. So the height will be halved. So 0.037 into 2.8 by 2 square by t, because 2.8 is because you have to consider the clay layer below the footing B. So, this comes out to be 0.036 meter square per year. So, this is the coefficient of consolidation that we found out. Now, you are asked to find out the 24 millimeter defense settlement. You considered the H just below under footing B, because as I have said previously also that you have already considered the clay layer to be of 1.2 meter thickness. So, all questions or all calculations regarding 1.2 meter thickness are accurate, but because of this extra 2.8 meter that came, all your calculations are now out of bounds, because all your calculations are now wrong, because this extra 2.8 meter has caused a difference settlement of 57.5 millimeter. So, that is why that is the extra layer that you have to consider when calculating all these coefficient of consolidations, because the coefficient of consolidation during that period only you have to consider. The 10 millimeter already has been, the 10 millimeter can be achieved in both the layers. The 10 millimeter can be achieved, the 10 millimeter difference settlement is due to the excessive settlement under footing B, but not under footing A. So, that is why we considered a 2.8 meter rather than considering 1.2 meter. Now, for 24 millimeter difference settlement, we again have to find out what is the degree of consolidation for 24 millimeter difference settlement. So, again delta by delta U. So, 24 and your ultimate is 57.5 millimeters. So, it comes out to be 0.42 or 42%. Now, since U is again less than 60%, so again your TV comes out to be 4 by pi into U by 100 square. So, which comes out to be 4 by pi into 42 by 100 square. So, which comes out to be 0.225. Now, just rearranging this formula, you have found out what is the coefficient of consolidation CV for settlement for basically as difference settlement of 10 millimeter or the 10 millimeter, which is the present ongoing defense settlement. Now, considering the defense settlement of greater than 10 millimeter or 24 millimeter, TV into H square by CV, the time required to know that at what time the defense settlement will occur. So, TV as I found out is 0.036 meter square per year. So, 0.036, TV is obviously 0.225. So, 0.225 and H is again 2.8 by 2, because I have said that all the calculations that you have to consider is due to that extra 2.8 meter layer below footing B, because that is the only layer that is considering the defense settlement. So, 12.25 years. So, 12.25 years, for 12.25 years your building is actually within the permissible defense settlement limit, but after 12.25 years your building will not be within the permissible defense settlement limit. So, the extras in the coming to 10.25 years, your total defense settlement would reach 24 millimeter. If you calculate, you will see that this 10 millimeter, considering the coefficient of consolidation CV, if you calculate this 10 millimeter, you will see that this in 10 millimeter has actually been achieved in 2 years. This 10 millimeter defense settlement is actually achieved in 2 years. So, that is why it is said that in the extra 10.25 years the total defense settlement would reach 24 millimeter. So, you can see that how a defense settlement is actually very detrimental to a structure. Now, we will consider just another problem before going on to the next chapter. This also is not exactly on defense settlement, I would say, rather this is about how, if you have an uneven soil profile, you have to calculate the settlement at different points in the soil profile. So, that is why I have said from the beginning that in order to know, since settlement is very important to a structure, as you will know from all the Indian standard codes. If you consider in Indian standard codes, you will know that the settlement is very detrimental to the structure. Also, above shear strength means above testing of footing for whether the soil can hold its strength or not. The next important factor that you have to consider is whether the structure would allow a settlement within permissible limit or not. That is why an extensive soil investigation is always required by constructing different holes and the soil profile in order to know the exact profile of the soil. A soil profile is not uniform everywhere as you see in problems, rather it is very different than you see in problems. So, in a third problem illustrating the effects about how it would be is described here. So, this is a levee and here is a normally consolidated clay layer. Now, since it is a normally consolidated clay, so obviously the effect of pre-consolidation now will not consider, we will only consider the virgin consolidation curve. So, that means we can approach both by the coefficient of volume compressibility method as well as by the coefficient of compression index method in order to calculate the settlement. Now, you see here that the soil profile again is not uniform. So, the different depths, so generally how in actual life how it is done is that, let us say you construct a borehole here. So, here you find out that the soft normally consolidated clay has a height of 2.8 meter. In the next case, you consider it at here and you construct a borehole and you find out that is 3.2 meter. So, this is at point A, this is point B. At here you construct another part and this is 4 meter, this is C, then there is a 4.4 meter, this is D and this is 5 meter, this is E. Now, what you do is that you have these soil profiles. So, you have the complete soil profiles at, let us say, at point A, point B, point C, point D, point E. You just join these points because you know what is the depth of normally consolidated at each of these points, you join these points and you get an approximate soil profile. Then there is a layer of sand and gravel and there is an impervious stiff. Now, you see, in all the previous problems that we have discussed, we considered that the load that is imparted on the structure is actually constant, only the soil profile is varying. In this case, however, you see that the levee itself is uneven, that means the load that is imparted on the soil due to the structure is non-uniform. So, in this case, let us consider that this height length is 12 meter, this length is 4 meter and this length is 12 meter, that means it is symmetric about the center. The water table is at a height of 5 meter from the depth of normally consolidated clay and this total height is 6 meter. So, now you can see that the soil data is extremely limited. Now, it is given that whatever the soil data, now another important problem is that the soil data that is given here, it is not always possible to calculate this consolidation and all these data. So, if you are given to evaluate the compression index and coefficient of consolidation very fast, in that case basically you have to take help of different formulas that we also did in the previous problems like liquid limit, plastic limit, all those cases, and we can generally evaluate the compression index or the coefficient of compression from all these cases. So, in this case the soil data is entirely limited and it is given that the W or the water content of the soil is 55.6%. Obviously, this is of the clay layer because the clay layer is the only layer that will settle under the consolidation. The liquid limit is 68% and the plastic limit is 30%. Now, what we will do is there, first you have to know that how to find out the compression index. So, obviously, the compression index can be found out from 0.009 into LL minus 10 for this clay layer and it is equivalent to 0.009 and LL is given as 68 minus 10. This is equivalent to 0.52. So, this part for consolidation has been known. Now, you can also find out E naught because E naught is equal to W into GS and it is already given that this entire layer is below the water table. So, W you know is obviously 0.556 and GS is given as 2.7. So, this comes out to be 1.5. So, E naught is also found out. H is obviously varying at different depths. The question here is that how do you find out the vertical stress distribution, because as I have said that the structure, that the load that is imparted on the soil is non-uniform and the structure itself is not uniform. It is symmetric, alright, but it is not uniform throughout. So, you can use a combination of a surface strip load with uniform stress distribution. That is how you generally approach the problem. So, in that case basically what you do is that you consider it to be like this. Rather than considering it to be a levy of like this, you consider it to be of like this, and you find out the stress at this point due to the layer. Now as I have said here, only gamma into H are the two combination that is going to be considered here. So if you consider uniform surface strip load, then in that case you can find out the QS that is generated at each point. So let us first consider, so we will consider only this point and this point, because all the other points we already know. Since we already know the soil profile is given to you, so we will consider only at this point what is the depth, then at this point what is the depth. So primarily your QS at this point would be equivalent to 108 kPa if you find it out from gamma. Now obviously you have to find out the gamma dash for the profile. So gamma dash will be equivalent to G minus 1 into gamma W by 1 plus E. So this is equivalent to 6.7 Newton per meter cube. At the center of the embankment it will be equivalent to 108 kPa, and here also it will be equivalent to 108 kPa. Now delta sigma z, that is the stress imparted due to the additional part, will be equivalent to 49.4 and 52.7. Now how did I find out this number? Now these numbers you will come across in later part, where basically we will discuss the distribution of stress on soils. In that case we will say that if there is an embankment like this, then depending on the position of the point where you want to find out the stress, let us say this, if this point is Z, there are charts available, or you can use formulas like the previous formula that I used in case of a rectangle. This formula, like the previous formula that I used in case of a rectangle, in this case you can also find out the stress below an embankment, the delta sigma z, from a formula. So in this case I am not discussing the details of the formula, but I am just showing you an example about how you can find out. So the stress on the either side of the embankment will be different, and that is what it is written, that 49.4 and 52.7 at this point, 88.4 at the midpoint, and 51 and 47.8 at the end point. Now width and Z is given as 1.6 meter, 2 meter and 2.2 meter. Now obviously these points are, as I have said, at this point 2, 1, 3. Now these are all, remember these Z's are always the half width, because the actual, because you have to find out the settlement at the mid height. So that is why I took Z as 1.6 meter. So 1.6 meter because is at this point 3.2, 4 in between the levee, and 4.4 at the end. So this is 2.2 meter. So a little soil profile, if you consider, it's like this actually. So at this point the height is 3.2 meter, mid height it is 4 meter, and at this point it is 4.4 meter. So this is how the soil profile looks like, and I have approximated it to be like this, with this side, and this point. I am finding out the stresses at this point, and this point. So here the height is 1.6, 2 and 2.2. So you know that the extra stress that is imparted here is 49.4 and 52.7, and I have ignored the formula here. Let us assume for the timing that this data is actually given to you. This is 88.4 and this is 51 and 47.8. This is delta sigma z, and this is the z. Now if these three things are known to you, then how do you calculate the settlements? So the settlement, so basically if the settlement is, so as I have said that the soil is normally consolidated. So obviously the only settlement that you will come across is H into Cc by 1 plus E naught into log of sigma naught dash plus del sigma by sigma naught dash. Now H is varying, because H for the leftmost case is 3.2 meter, for the middle it is 4 meter, and for the end is 4.4 meter. So let us form from a table. So, point 1, 2, 3. 1 point is the most point, 2 is the middle point, 3 is the rightmost point. So, in that case delta sigma z is given to you as 49.4 plus 52.7, which is equivalent to 105.6, 102.1 and 98.8. So, these are the delta sigma z that are given to you right now, and sigma z naught dash is 13.4, 10.7 and 14.7. Now, this you can easily find out because you know that what is the height of the clay layer at this point, and basically multiply it by gamma. So, let us say that your gamma is 6.7 and you just multiplied 6.7 with 3.2. So, at mid height of the clay layer, so that means 6.7 with 1.6 and you will get 13.4, similarly with 2 and similarly with 2.2. So, once you multiply all these things, then the sigma final will be equivalent to, or sigma naught plus delta sigma will be equal to 119, 112.8 and 113.5. Now, just plug these values and you will see that a settlement profile like this is obtained. So, this one is 0.68, this one is 0.79 and this one is 0.81, let us say, it will be more. So, you see that the settlement profile here is again non-uniform in nature. Now, this is, let me tell you that this is a demonstrative problem, because there are many parts of this problem that are till not discussed. So, like the how to find out the stress below, find out the stress below an embankment. So, that is why I have ignored all the calculations here. I just showed you that how basically if there is a non-uniform soil profile, how basically you find out the how basically you can see or you can visualize the settlement below a non-uniform structure. So, in this case the non-uniform structure is the levee, and in this case you can see that this is the settlement profile. So, initially let us move back to the problem that there was a soft non-linear consolidated clay and there were there was an extensive soil investigation that was carried out, but data were not available. So, we just considered only the water content, the liquid limit, plastic limit that can be easily obtained from the fields were discussed. So, in this case we found out what is the value of Cc, what is the value of E naught, and then we moved to the part where basically the how to consider the vertical stress distribution. So, in this case we said that I said that the levee is to be considered to be an embankment with different heights, with embankment with a uniform surcharge, considering a uniform surcharge with uniform stress distribution, and then you divide the embankment into 3 sections and find out the stress below each of these sections. So, in this case when you found out the stress below each of these sections, then delta sigma z came out to be 105.6, 102.1, 98.8 respectively for the 3 cases, and delta sigma z naught is nothing but actually the stress at the mid height of the clay layer. Now, since the 3 depths are different, so that is why it was multiplied with gamma dash or the submerged unit weight to obtain the different depths, and the sigma final was obtained accordingly just by adding these 2 numbers. Considering those facts, now considering the settlement equation, since it is a normally consolidated, considering the settlement equation H into Cc by 1 plus E naught into log of sigma naught dash plus del sigma by sigma naught dash, we just plotted that how the settlement profile would look like, and we saw that the settlement profile somewhat looks like this, where this one was found out to be 0.81, this one was found out to be 0.79 and this one was found out to be 0.68. That means the settlement profile is non-uniform, and in this case also you have to see that what is the permissible difference in settlement, since it is the arch structure. So, what is the permissible difference settlement for the arch structure that you can permit? Remember that in considering all these cases, I have only considered 3 points, but you can consider points more than 3. In fact, you can consider even all these 5 points that are considered 2.8, 3.2, 4, 4.4, 5.5. There is no problem regarding this, but 2.8 and all these things are actually far out of the levee, rather than 3.2, 4 and 4.4 are the only 3 points that are within the levee. So, that is why we considered only these 3 points. So, we will stop the consolidation problem here today, and in the next class we will discuss about the shear strength of soils, which will be the last tutorial session. Thank you.